Choosing good augmenting paths. In the previous section, we saw that any way of choosing an augmenting path increases the value of the flow, and this led to a bound of C on the number of augmentations, where C is equals to the summations of CE summing for OE out of S. When C is not very large, this can be a reasonable bound. However, it is very weak when C is large. To get a sense for how bad this bound can be, consider the example graph in figure 7.2, but this time assume the capacities are as follows. The edges S, V, S, U, V, T, and U, T have capacity 100, and the edge U, V have capacity 1, as shown in figure 7.6. It is easy to see that the maximum flow has value 200 and has f of e equals to 100. For the edge S, V, S, U, Vt, and Ut, and a value of 0 on the edge UV. This flow can be obtained by a sequence of two augmentations, using the paths of nodes S, Ut, and the path S, Vt. But consider how bad the Ford-Fulkerson algorithm can be with the pathological choices for the augmenting paths. Suppose we start with the augmenting path P1 of nodes S, U, V, T in this order as shown in figure 7.6. This path has bottleneck P1F equals to 1. After this augmentation, we have f of e equals to 1 on the edge e equals to uv, so the reverse edge is in the residual graph. For the next augmenting path, we choose the path P2 of the nodes S, V, U, T in this order. In this second augmentation, we get bottleneck of P2, f equals to 1 as well. After this second augmentation, we have f of e equals to 0 for the edge equals to uv, so the edge is again in the residual graph. Suppose we alternate between choosing P1 and P2 for augmentation. In this case, each augmentation will have 1 as the bottleneck capacity, and it will take 200 augmentations to get the desired flow of value 200. This is exactly the bound we proved in 7.4, since C equals to 200 in this example. Designing a faster flow algorithm. The goal of this section is to show that with a better choice of paths, we can improve this bound significantly. A large amount of work has been devoted to finding good ways of choosing augmenting paths in the maximum flow problem so as to minimize the number of iterations. We focus here on the one of the most natural approaches and will mention other approaches at the end of this session. Recall that augmentation increases the value of the maximum flow by the bottleneck capacity of the second path. So if we choose paths with large bottleneck capacity, we will be making a lot of progress. The natural idea is to select the path that has the largest bottleneck capacity. Having to find such paths can slow down each individual iteration by quite a bit. We will avoid this slowdown by not worrying about selecting the path that has exactly the largest bottleneck capacity. Instead, we will maintain a so-called scaling parameter delta, and we will look for paths that have bottleneck capacity of at least delta. Let GF of delta be the subset of the residual graph consisting only of edges with the residual capacity of at least delta. We will work with values of delta that are powers of 2. The algorithm is as follows. Scaling maximum flow. Initially, we set up f of e equals to 0 for all edge e in G. Initially, we set delta to the largest power of 2, that is no larger than the maximum capacity out of S. That is, delta is less than or equals to the maxima taken of CE, where the maxima is measuring for OHE out of S. Now, while delta is greater than or equals to 1, then there is another while loop, while there is an ST path in the graph GF of delta. Let P be a simple ST path in GF of delta. Then f prime equals to augment of fp. Updated f to be f prime and update GF of delta. Then end while. After we break out from the inner while, we have to adjust the value of delta. So we set up the delta equals to original delta divided by 2. Then, after we break out the outer while loop, we return f, the flow. So analyzing the algorithm. First, observe that the new scaling max flow algorithm is really just an implementation of the original Ford-Fulkerson algorithm. The new loops, the value of delta, and the restricted residual graph gf of delta are only used to guide the selection of a residual path with the goal of using edges with large residual capacity for as long as possible. Hence, all the properties that we proved about the original max flow algorithm are also true for this new version. The flow remains integer valued throughout the algorithm, and hence all residual capacities are integer valued. 7.15. If the capacities are integer valued, then throughout the scaling max flow algorithm, the flow and the residual capacities remain integer valued. This implies that when delta equals to 1, gf of delta is the same as gf, and hence when the algorithm terminates the flow, f is a maximum value. Next, we consider the running time. We call an iteration of the outside while loop with a fixed value of delta. We call it the delta scaling phase. It is easy to give an upper bound on the number of different delta scaling phases in terms of the value c equals to the summations of ce summing for all e out of s that we also used in the previous section. The initial value of delta is at most c. It drops by factors of 2, and then it never gets below 1. Thus, 7.16. The number of iterations of the outer while loop is at most 1 plus the sitting functions of input of log 2 of c, base 2 of c. The harder part to count the number of augmentation done in each scaling phase. The idea here is that we are using paths that augment the flow by a lot, and so there should be relatively few augmentations. During the delta scaling phase, we only use edges with the residual capacity of at least delta. Using 7.3, we have 7.17. During the delta scaling phase, each augmentation increases the flow value by at least delta. The key insight is that at the end of the delta scaling phase, the flow f cannot be too far from the maximum possible value. 7.18. Let f be the flow at the end of the delta scaling phase. There is an ST cut AB in G for which C of AB is less than or equals to V of f plus m times delta, where m is the number of edges in the graph G. Consequently, the maximum flow in the network has value at most V of f plus m times delta. This proof is analogous to our proof of 7.9, which established that the flow returned by the original max flow algorithm is of maximum value. As in that proof, we must identify a cut AB with the desired property. Let A denote the set of all nodes V in G for which there is an SV path in GF of delta. That B denote the set of all other nodes, that is B equals to V minus A. We can see that AB is indeed an ST cut, as otherwise the phase would not have ended. Now consider an H equals to UV in G for which U is in A and V is in B. We claim that the capacity CE is less than f of E plus delta. For if this were not the case, then E would be a forward edge in the graph GF of delta, and since U is in A, there is an SU path in GF of delta. Appending E to this path, we would obtain an SV path in GF of delta, contradicting our assumption that V is in B. Similarly, we claim that for any edge E prime equals to U prime V prime in G, for which U prime is in B and V prime is in A, we have f of E prime is less than delta. Indeed, if f of E prime is greater than or equals to delta, then E prime would give rise to a backward edge E prime prime equals to V prime U prime, in the graph gf of delta, and since v prime in A, there is an s v prime path in gf of delta. Appending e prime prime to this path, we would obtain an s u prime path in gf of delta, contradicting our assumption that u prime is in B. So all edges E out of A are almost saturated. They satisfy CE, which is less than f of E plus delta, and all edges into A are almost empty. They satisfy f of E, which is less than delta. We now use 7.6 to reach the desired conclusion. V of f is equals to the summations of fe summing for all E out of A minus the summations of f of E summing for all E into A, which is greater than or equals to the summations of C minus delta summing for all E out of A minus the summations of delta summing for all E into A, which is equals to, if we separate the CE minus delta from the first summation, that is equals to the summations of CE summing for all E out of A minus the summations of delta summing for all E out of A, then minus the summations of delta summing for all E into A. That is, which is greater than or equals to the capacity between A and B minus m times delta. Here, the first inequality follows from our bounds on the flow values of edges across the cut. And the second inequality follows from the simple fact that the graph only contains m edges total. The maximum flow value is bounded by the capacity of any cut by 7.8. We use the cut AB to obtain the bound claimed in the second statement. 7.19. The number of augmentations in a scaling phase is at most 2m. Proof. The statement is clearly true in the first scaling phase. We can use each of the edges out of S only for at most one augmentation in that phase. Now consider a later scaling phase delta and let Fp be a flow at the end of the previous scaling phase. In that phase, we use delta prime equals to 2 times delta as our parameter. By 7.18, the maximum flow F star is at most, that is V of F star, which is less than or equals to V of Fp plus m times delta prime, which is equals to V of Fp plus 2 times m times delta. In the delta scaling phase, each augmentation increases the flow by at least delta, and hence there can be at most 2m augmentations. An augmentation takes big O of m time, including the time required to set up the graph and find the appropriate path. We have at most 1 plus the scaling functions of log base 2 of c scaling phases and at most 2m augmentations in each scaling phase. Thus, we have the following result. 7.20. The scaling max flow algorithm in a graph with m edges and integer capacities finds a maximum flow in at most 2m times 1 plus the scaling functions of a log base 2 of c augmentations. It can be implemented to run in at most big O of m squared times log base 2 of c time. When c is large, this time bound is much better than big O of m times c bound that applied to an arbitrary implementation of the Ford-Fulkerson algorithm. In our example at the beginning of this section, we had capacities of size 100, but we could just as well have used the capacities of size 2 to the 100. In this case, the generic Ford-Fulkerson algorithm could take time proportional to 2 to the 100, while the scaling algorithm will take time proportional to log 2 of 2 to the 100, which is equals to 100. One way to view this distinction is as follows. The generic Ford-Fulkerson algorithm requires time proportional to the magnitude of the capacities, while the scaling algorithm only requires time proportional to the number of bits needed to specify the capacities in the input to the problem. As a result, the scaling algorithm is running in time polynomial in the size of the input, i.e. the number of edges and the numerical representation of the capacities, and so it meets our traditional goal of achieving a polynomial time algorithm.
Bad implementations of the Ford-Fulkerson algorithm, which can require close to C iterations, do not meet this standard of polynomiality. Recall that in section 6.4, we used the term pseudopolynomial to describe such algorithms, which are polynomial in the magnitudes of the input numbers, but not in the number of bits needed to represent them. Extensions. Strongly polynomial algorithms. Could we ask for something qualitatively better than what the scaling algorithm guarantees? Here is one thing we could hope for. Our example graph, figure 7.6, had 4 nodes and 5 edges, so it would be nice to use a number of iterations, that is a polynomial, in the numbers 4 and 5, completely independently of the values of the capacities. Such an algorithm, which is polynomial in the size of V and the size of V only, and works with the numbers having a polynomial number of bits, is scaled a strongly polynomial algorithm. In fact, there is a simple and natural implementation of the Ford-Fulkerson algorithm that leads to such a strongly polynomial bound. Each iteration chooses the augmenting path with the fewest number of edges. Dinitz and independently Edmonds and Karp proved that with this choice, the algorithm terminates in at most big O of m times n iterations. In fact, these were the first polynomial algorithms for the maximum flow problem. There has since been a huge amount of work devoted to improving the running times of maximum flow algorithms. There are currently algorithms that achieve running times of big O of m times n times log n, and big O of n to the cube, and big O of the minima chosen among n to the 2 over 3 and m to the 1 over 2 times m times log n times log u, where the last bound assumes that all capacities are integral and at most u. In the next section, we will discuss a strongly polynomial maximum flow algorithm based on a different principle.